It is beyond a shadow of a doubt, my friends, that it is an extraordinarily beautiful early morning here in South Carolina. And as is and shall always be the case in perpetuity, it is my sincerest wish that things are equally as beautiful for you and yours in your neck of the woods. And the topic of today's video lecture is as follows: an introduction to physics, the gravitational acceleration constant. Okay, let's dive into this. The most generic example of the force equation is Newton's simple F equals ma equation, where F stands for force, so it's the SI symbol for force. Oh no, that's wrong. Force, which is measured in newtons. And I think in a separate video I went into the SI units, and if I didn't, then one of these videos will be due. But suffice it to say that force is measured in newtons, mass in SI units will be measured in kilograms, mass, and the acceleration constant, which when you multiply these two terms together will give you the magnitude of what any force is. Okay, but when we're dealing with objects near the Earth's surface, we will have a force which can be denoted with F and a subscript of W for weight, as is often seen in textbooks or in other places. But the force of weight, or the weight of an object, is a multiple of the mass of the object and the gravitational constant of acceleration near the Earth's surface. And that gravitational constant of acceleration is 9.8 meters per second squared. Where does all of this come from? Well, G is equal to 9.8 meters per second each second. And what I should have written here is that when dealing with an acceleration, you're dealing with a change of velocity. A change. I should have put a little delta in there. Change, 9.8 meters per second. It's changing by that much each second. Okay, and if we rewrite what we have here in a form that's more intuitive, which is what we have right here, which is 9.8 meters per second each second. And if we take this term and put it in brackets to be multiplied by another term, or the seconds term right here, we have a very useful expression in which we can find out after any number of seconds how fast an object that is falling towards the surface of the Earth will be moving. Okay, 9.8, for example, 9.8 meters per second each second times, let's say, 2 seconds. After 2 seconds, if we do the math, you see that seconds will cancel out. 2 times 9.8 is going to be, I think, 19.6. So after 2 seconds, the object would have an instantaneous velocity of 19.6 meters per second. After 3 seconds, 19.6 plus 9, 28 point. It's going to be around 29 meters per second. But that pretty much explains why, or it shows the usefulness of looking at the equation in its expanded form. But let's move on forward here and further examine why this is the case and where the equation from which this comes from. And it's a very common equation that you will see very early on in any physics class and many other classes as well, engineering, even perhaps in some biological systems, or definitely in biochemistry, one of my favorite classes in college, by the way. But we have, okay, right here, this equation, the force of gravity, F sub G, is equal to a gravitational constant, and I don't remember what that is. It's 9 or 6 point something or whatnot, 6.8. But suffice it to say, some gravitational constant that doesn't change. And then one mass, M1, times another mass that are separated by some distance, and that distance is going to be squared. And when you do all of the math, what you end up with is some expression that's going to be expressed in newtons. But for the sake of finding out where this particular, or the derivation we finished looking at comes from, let's assume that M1 right here is going to be the mass of the Earth, big M sub E. And let M2 equal mx. M2 or mx could be, who knows, a baseball that's fallen, a monkey that's jumped out of a tree, somebody. It could be anything. But it's near the Earth's surface, and it's so much smaller than the mass of the Earth that we will be able to take an approach that is very intuitively satisfying and simplifies into the equation that we just finished looking at. And see that right here. So if we take FW, which is a gravitational force right here, but I'm writing it with F sub W because the derivation that I'm going to do here involves a mass, the mass of the Earth. And it's going to show or give us an equation that quantifies the force, the magnitude of the force. So we still have the gravitational constant of acceleration right here. And, well, now within the equation, we substitute the mass of the Earth and the r squared term right here. And notice that we now have three constants that aren't going to change. The gravitational constant of acceleration, when dealing with things near the masses near the Earth's surface, and taking this equation into account, this isn't going to change. The radius of the Earth, where you start measuring at the center and move outward towards the surface, that's not going to change. And so since these three constants all have values that don't change, when you do the multiplication between these two constants, and then you divide by the radius of the Earth squared, what you end up with is the G term. G equals 9.8 meters per second squared. And, well, right here we have this term where all the math has been done. You end up with G here, m to the x here. And then you just rearrange it to make the term more familiar with what we have seen beforehand. All right, moving right forward here. If we have a circumstance, and this will further make the equation and its usefulness in quantifying force on the amount of mass that is falling towards the Earth, this is going to make it even more reasonable. If we have right here something that has a weight in newtons, and it has a mass, and it is it's accelerating at 9.8 meters per second squared, it's going to be less. The force at which, like if you had to catch this, as opposed to something that's falling and it's 5 times as massive. Look at what happens with these equations. The G term here and here don't change. But if we take the mass and make it 5 times larger as what was done here, then the amount of force that the gravitational force of attraction on this object that is 5 times more massive is going to be 5 times greater. And that makes sense when you think in terms of picking something up. Like if you had to pick up this object versus this object, you would have to apply 5 times as much force to move it upward and away from the Earth's surface. So in turn, when it is released, it's going to move down with 5 times more force, but with the same acceleration. And the reason that this is true is that mass is a measure of inertia. Inertia meaning a resistance to being moved, or if something is already in motion, a resistance to being taken out of motion or decelerated. And I have a diagram that will make all of that a little more clear right here. Okay, look at this. We have a mass right here that is accelerating towards the Earth. Right here we have 3 separate masses, each one of them being acted upon by the same magnitude of force, bringing them down. So it only makes intuitive sense that if these 3 masses were combined, then what we're going to have is 3 times the amount of force acting upon that mass as we would 3 separately right here, or each one of these, or this singular mass located right here. Okay, folks, and for further excellent mathematical examples, calculus, statistics, so forth, so more, and beyond, please check out the Peter C. Dorkpo Jr. Excellent Tutoring Institute on YouTube. And for more STEM content that spans the entire spectrum of scientific learning and thought, please also review the contents on the excellent Liberian Math, Science, and Engineering Scholars page on Facebook. Best of luck in all of your studies and with your life endeavors as well. Goodbye.